recording. Okay, I thought before we begin, I've had a few questions recently on the project, and I thought I would just address them like together so that the answers are common. So one of the questions I got asked was about mass stand. And the question was, can you use mass stand to do the real and virtual analysis when you're doing that part of the project? And I'm not a micromanager, so sure, but what you have to recognize is that you are depriving yourself of another means of verifying your answer. So the initial thought behind the project was that you would do the analysis by hand and then verify your answers with Mastan. But if you want to do that analysis in Mastan, the real analysis and the virtual analysis to assess your deflections and whatnot, I have no problem with that whatsoever. But just know that if it's wrong, you don't have another way of checking it. Do you know what I mean? So I have no problem with that. Let's see. I had another question. I think it was from Mr. Brown about the CAD drawing. What was your question, if you don't mind me asking?
The placement of the steel price and the design constraints.
Well, first off, it was. Did the CAD example that I give did that not answer it, or what was the question?
Is the CAD example included on the
yes
middle too? I couldn't find it as a second page. I only found the.
Did I not include it?
I'll check again.
If I didn't include that, my apologies. I will if I didn't, because what I should have done. Hold on. Let me see. Please tell me it was on there. I'll be mad at myself if it wasn't. Oh, I bet when I updated it, I didn't put it on there. My apologies. I will submit that. What it was supposed to look like was this. That's what was supposed to be on there. I will upload this. My sincere apologies. But yeah, I wanted the design notes and constraints right there. My apologies. I will have this uploaded today. Okay, did I miss a question on the project? I know I had one student ask me like a specific question about their project, but any global questions about the project that I missed? How many of you started working on it? Okay, we got a few. All right. If you haven't started it, I probably would. Because I don't want you to feel rushed at the last minute. I genuinely don't. On Wednesday of next week, we are going to have a devoted Q&A session just for the project. So I want you all to, so one thing I did not put on here was the schedule for the next few weeks. And usually I do that on my announcement slide when we have an exam coming up. But we don't have any more exams in here other than the final. So here's what is going to be like for the next few days. Today we're doing a third influence line lecture on dealing with fixed supports, and I'm going to show you influence lines for trusses. Okay, so what are we going to talk about Friday? Friday we're going to talk about Friday we're going to talk about applying influence lines. I've been talking about how to draw them, but we haven't really used them. So Friday we're going to use them. And Monday, we're going to talk about AASHTO. How many of you have had transportation and have heard the term AASHTO before? Okay, so what we're going to be talking about is AASHTO load models for designing bridges and how we use influence lines to do structural analysis of bridges according to AASHTO load principles. That's what we're going to talk about on Monday. So today, fixed supports and trusses. Friday, applying influence lines. Monday's bridges. Wednesday of next week, we're going to have a troubleshooting and Q&A session just for the project. So my strong suggestion for you is that between now and then, I would really put some work in on your project so that you can come to class and ask questions. I'm going to be completely blunt with you. Next Wednesday, I'm not taking attendance. So come or don't, okay? I'm not recording that session either because it's just a troubleshooting session for the project. If you feel good, you don't have to come. If you've got questions about the project, come and ask them. We'll go through them. Friday of next week, no class. You okay with that? Then Monday and Wednesday of dead week, I've got 2 topics that I would call real life topics I want to do near the end. And then we'll have our final. We're done with this class. What do you think? We can write this one off. Okay, let's do some fixed supports. Now, I would argue that these problems with fixed supports are the easiest problems and also the ones that students tend to screw up the most. Okay? You got to pay attention to what's going on the structure. And I think what happens more often than not with influence lines related to fixed supports is that students tend to invent stuff that isn't there, okay? And you'll understand what I mean when we start going into some of these examples. So, the Mueller-Breslau principle is a graphical approach that says the deflected shape of a structure represents to the same scale, or to some scale, the influence line of a force effect if the quantity in question is moved through a small unit displacement. Identify the response of interest, remove from the structure the ability to resist that response, move it through a unit displacement. Now, we need to talk about fixed supports, okay, because this is important, okay? None of the rules that we've derived are invalid for fixed supports. They work just fine, but they do require some further review, and you got to pay attention, okay? So, I want to consider the influence line for this fixed support. Now, y'all might want to watch this, okay? We are considering the influence line for the vertical reaction. And I want to be clear, only the vertical reaction, okay? When you draw an influence line, you draw an influence line for a response of interest. So all I'm considering is this. Now tell me how the Mueller-Breslau principle works. We remove from the structure the ability to withstand this, and we move it through a unit translation. What we do not do is remove this. This stays, this goes. So if I take that element and I move it through a translation, I do not rotate it. I lift it, but I don't rotate it. So if you're drawing your influence line and you're doing that, that's wrong, because you are taking this point and lifting it and rotating it. We're not doing that, okay? This is a fixed support. The moment reaction didn't go anywhere. That moment reaction is whatever special value is required to prevent rotation at that support. And that moment reaction didn't get removed. That's incorrect. That's correct. Okay? We move it through a unit translation, not a unit translation and some arbitrary rotation as well. Does that make sense? This is my little prop I'm going to use here in a little bit. So for moment reactions, if I wanted to draw an influence line for the moment reaction, I would remove from the structure the ability to resist that moment. And I rotate it, but I don't translate it. So for the moment reaction, it would like just do that. But it wouldn't move, it would just do that. Does that make sense? Let's do the influence line for this beam. It's just a cantilevered beam. We're going to do the vertical reactions, and we're going to do the shear and moment too. We're going to do that because why not? I didn't screen cap this before. I was not prepared. I know, shame on me. That's not a mistake. I didn't do anything wrong, per se.
Is it half a power point?
I think it's about 0.06.
I'll round that to 0.1.
All these rounding errors, just saying. Okay. All right, so we're going to draw an influence line for reactions as well as internal response at this point. Okay? Now, I'm just going to redraw the structure. This one we can sketch by hand. We don't need to be super hyper cognizant of, you know, our scale and rulers and all of that. So I'm just going to draw this one by hand. Okay. So here's the structure. So we'll call this right here section B. Here's our support. This is AY. Now, for our moment, now this is an interesting thing about moment. So one of the things that is conventional with moment influence line, for moment reaction influence lines, is that you indicate your positive sign convention. When you see the homework assignment, you'll see that I've told you to assume counterclockwise moments are positive, but you'll see what I mean here in a little bit. That's not that big of a deal. Okay, so the other thing to keep in mind is that this is ten feet apiece. Okay. Okay, so I've drawn my guidelines, and let's do the influence line for the reaction at A first. Now, the first thing we're going to do is we're going to draw that influence line, then we're going to see if it makes sense. Because I don't want to just draw an influence line and go, oh, there it is, move on. We're engineers. I want us to understand what we're doing. So, if I take point A, remove from the structure the ability to resist the vertical reaction at point A, but not the moment, and I move it through a translation, what am I doing to this beam? So I have to pick point A up, but it can't rotate. Picking the whole thing up. So the influence line for the reaction at A looks like this. Boom. That's the influence line for the reaction at A. Now, does that make sense? Well, let me ask you a question. Let's say I have a cantilevered beam, and I put a 20 kip load right there. What's that vertical reaction? 20 kips. Okay. What if I put a 20 kip load right there? What's the vertical reaction? What if I put a 20 kip load right there? What's the vertical reaction? So what you're telling me is that if I take a single unit load of 1.0 and I move it along the structure, it does not matter where I place that load along the beam, the vertical reaction is 1 everywhere. Is that what you're telling me? Isn't that what the influence line says? The vertical reaction is 1 everywhere along the beam? Did I miss something? How'd I do? Okay. Now, let's do the moment at A. And what we'll do is we'll do our rotation like this. Actually, let me roll that down a little bit. So again, with moment influence lines, it is typical that you indicate your axis of rotation or your direction of rotation. So this is saying counterclockwise positive, and you'll see what it means if you do clockwise positive. So here's what we're going to do. We're going to take point A and we are going to rotate it, but we're not going to translate it. So what would the beam look like if I took this point and rotated it? And rotated it this way? It'd just go like that, wouldn't it? Boom. That's the influence line. Now, the $64,000 question is, if this is the influence line, what's that value right there? How much am I rotating it? One. Now, what does that mean? What does it mean to rotate it one? It means to rotate it to such an angle that the slope is 1. Now, I ask you, if the slope of that line is 1, what's that value? 20. Now, does that make sense here? Well, let's see. Let's say that the beam is 20 feet long, okay? And let's say I put a single unit load 6 feet away. What's the vertical reaction? What's the moment reaction? And how did you get that? Well, the air, that's one way. So you can integrate the shear diagram, or 1 times 6 this way, 1 times 6 this way. Am I right? So what if I did, I don't know, 1.0 and this was 17? It'd be 17, right? And if I had the load right here, the moment reaction is 20. Does that make sense? So the moment reaction is going to be linearly distributed, or the moment influence line is just going to be a line originating here from 0 to 20. Does that make sense? Now, if I had, more going on here, if I had like a roller and then I had a hinge, what would that look like? Like if I had a roller here and a hinge here, it might go up and down, but it would still just rotate up at a slope of 1. Does that make sense? Any questions? Now we're not done. And this is where you gotta really put your noggin on, really gotta pay attention. So I'm gonna cheat a little bit. Oh wait, I just want, oh God, I don't want that. I just want that. Technology. So now, I want to draw the influence lines for these internal responses. Okay. We're going to start with the shear at B. Okay. Now really put your thinking cap on here. I want you to pay attention. Here is the beam. And what we're doing for shear, now what did we do last time and what did you do on your homework assignment? We installed a shear release, right? And we trended the left side down and the right side up. Is that right? So does that mean that the influence line looks like this? Is that what that means? If you think that this is the answer, I want you to take your hand and do that. Because what you did is you rotated this point. I didn't remove from the structure the ability to resist reactions right here when I instituted a shear release, and yet you rotated it. Now, here's the problem, okay? So what does that mean, okay? So this side's got to go down, but this can't rotate. So this can't rotate, this can't translate, this got to go down. I don't know about you, but the only way that can happen is if that beam kind of curves. What do influence lines have to be for statically determinate structures? Linear. So that ain't going to work either. Now, how much is that total displacement got to be? That total jump? So what I need is a total jump of 1. I need the left side to tend downward. Doesn't have to go downward, just has to tend downward. And I need the right side to tend up. I need a total jump of 1, and that left side cannot translate or rotate. There's only one way that can work. That's the influence line for the shear at B. That's the only way it works. Now, does that pass the smell test for the real world? Well, let's see. Here's our beam. We got our reaction here. Reaction here. This is AY, MA. An influence line, we keep our eye fixed on a point of interest. In this case, the point of interest is the shear right at this samurai sword and or lightsaber, right? Okay? So, my eye is fixed right there. That's the only thing I'm paying attention to right now. Like my little green eye. Now, what do? I take a unit load and I move it across the structure. Now let's say the load is somewhere over here. Let's say this is 1. That makes this 1 as well, right? Now I'd like to samurai sword or lightsaber through that section. Which way you want to look? I don't care. Pick one. To the right. When the load is over here, what is V? There's nothing there, right? There's not a thing there. In fact, the entire time that the load is on this side of the line, I cut a section, look this way, V is 0. Every time the load is over here, V is 0. But what happens when that load just barely goes on the other side of that line? And I put that load right there. What happens to V? It jumps to 1, right? And that happens. Now, what is V if 1 is here, or here, or here, or here, or here? What's V?
1.
So we go from 0 to 1. That's your influence line for the shear at that point. Does that make sense? That is how you draw the influence line. Not only does it make sense from a rules standpoint, but it makes sense from a static standpoint. What do you think? All right. If that's the case, somebody tell me what you think this is going to look like.
0 to be angled over.
So yeah, 0, 0, and then it goes down like that. That's exactly right. We install a hinge at B, and our influence line goes here to that. Hold on, to that. What's the slope of that line? 1. So if the slope of that line is 1, what's the value right here?
Negative.
There you go. Now, why am I drawing the internal response negative? Because no matter where I place that load, the beam is wanting to frown. Negative bending moment. What do you think? I want to stop and see if anybody has any questions. Yes?
Would the slope be -1 or?
That's a fair question. Yeah, I guess you could say, yeah, the slope is technically -1. That's a fair point. Yeah, I guess we can say that. But the overall point is that we're undergoing a unit rotation. That's a fair point. The reason I'm drawing it negative, though, is because I know from context the beam will be in negative bending. It's a fair point. Any questions? All right. Am I okay to move on to trusses? Okay. All right. Now, here's the thing with trusses. So, and I'm not going to make you do this on the next homework assignment, so relax. But the thing with trusses is there's no shortcut. Like the Mueller-Breslau principle, and I want to be crystal clear, the Mueller-Breslau principle is a sound theoretical basis for drawing an influence line, but it is a graphical shortcut, and while the theory works for trusses, it's not like the concept doesn't work. In practice, it's very hard because you would have to, if I wanted to draw an influence line for the internal force in this member, I'd have to remove the member and then spread this out a unit of 1 and then see what the truss looks like. I don't know about you, but I can't do that in my head. I'm not that good. I don't know very many people that can. It works in concept, but it's very difficult to apply practically. And unfortunately, the only way that we really do influence lines for trusses is through brute force. And what do I mean by that? We have a truss, we put the load here, solve the truss. Put the load here, solve the truss. Put the load here, solve the truss. And just record the response. A pain, but it works. So the only thing that you have to pay attention to is, as an engineer, where are you going to apply the loads? And typically what we do is apply the loads where the road is. So on this truss, we would apply the loads like here, 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 along each of those joints. Now, why wouldn't I apply them at the supports? The internal response in the truss is going to be 0 if I put the load here or here. It's not going to do anything. So I would just need to put it here, here, and here. For this truss, I will put the loads along the top, right? That's where the road is. So I would put the load maybe like right here, 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 along every joint, and just record the response. And I'll show you how we would do this in Mastan, and I think you'll find this is really simple. So we're going to do this truss right here, and I'm going to do this member, and this member, but we can do plenty of them. It's really not that difficult. I'm just going to build this truss real quick in Mastan, and we'll show you how this works. So hold on. So just watch along with me. You'll see what I'm doing. So we're going to define some nodes. So define a node. define a node. And then this is 15 times 12. So here's my truss, or my joints. Now let's do the elements. Come on. Sorry if this is enthralling viewing, I know. Now, one of the things that isn't going to matter on this truss are what I would say the stiffness properties and the material properties, because this is a determinate structure. So whatever we define for E or A is not going to change the forces. It's going to change the deflections, but I'm not interested in the deflections. So there's that, and then I think the members went bam, 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 bam. Yep. So apply. So see, I'm sitting here doing this in the middle of class all the space of a few minutes. Your project component should be pretty easy. And again, notice how I'm defining from lower number to higher number. To be honest, doesn't really matter, but for axial members, but you'll want to do that on your project. Okay, define a section. Let's just pick a random one out of the database. Let's just pick, I don't know, that one. Hit apply. Attach the section to all members. Hit apply. Geometry or properties define material. Let's call it steel. Let's do 29,000. Hit apply. Properties attach material to all. Hit apply. So we've got our truss defined. We've got our properties, our section properties, and our materials attached. Now fixities. Node 1 is a pin support. Node 2 is a roller support. Okay. Okay, so here's our model. Okay, now let me ask you this. For this truss, is the road down here or is the road up here? It's on the bottom, right? So what that means is I need to do an analysis with the load right here, an analysis with the load right here, and an analysis with the load right here. So I need to do 3 separate analyses. So what I'll do is I'll place it, we'll go to conditions, forces. On joint 2, we'll do -1. A single unit load right there. And so, run an analysis. First order elastic, planar truss, apply, done. Okay, now in order to draw the influence line, what we're going to need to do is record some data. Okay, now I'm going to switch it up a little bit. We're going to do some different members. Let's do this member. So that's member AB. Okay, let's do this diagonal. Let's call that's CH. And let's do a compression member. Which one you want to do, the left or the right? Left. So that one's FG. All right. Okay, so what I'm doing is I'm placing the load at B, the load at C, the load at D. And what I'm going to do is record the response. So let's go to results, element forces. Now let's see. So if I put, let's see, for this element right here, it's saying the force is 1. For this diagonal, it's saying, what's it saying? 0.4167. And then for this one right here, it's saying negative 2/3, right? Does everybody see that? Okay. So now what I'm going to do is I'm going to delete that load. I'm going to put the load here, run the analysis, and record the data again, right? So I'm moving the load and doing the analysis. So define that as 0, define that, hold on, clear, define that, -1, hit apply, and then analyze the structure, results, element forces. So let's look at this one. So now this one is 2/3. Okay, the diagonal is 0.8333. And then this one up here is 4/3. Does everybody see that? Now, I'm curious. Anybody have a guess what's going here? 1/3. Let's see if you're right. So let's put the load there on that last joint. Well, look at that. 1/3. Okay? The diagonal, something interesting happens with diagonals. We get negative 0.4167, and then this compression member, negative 2/3. Does everybody follow along with what I'm doing? So I propose then that, let me screen cap that truss so we all kind of see what we're doing. So there's the truss. There's my pen. I propose that if I wanted to draw the influence line for member AB, it would be 0, 1, 2/3, 1/3, 0. Like that. Like that. That's the influence line. It's that simple. Does that make sense? All I'm doing is, it's kind of the brute force way. Like, I could do it by hand, right? I could put the load there, solve for the reaction, do method of joints, and then put the load there, solve for the reaction, do method of joints. Or I could let Mastan do the work. Either one works. Let's see what the diagonal does. Now, the diagonal is interesting. The diagonal goes 0.4167, the negative, and then back to 0. What happens with diagonals is that whenever you're moving the load across the structure, and by diagonals, I mean these internal members, what happens is whenever you move the load across the structure, when you go from one side of the diagonal to the other, you tend to change the sign. The internal diagonals are a lot like They respond a lot like shear does. That when you hop onto one end, you change the sign. It's very comparable to that. So this is going to be CH. And then the top members are the ones experiencing compression. So for member FG, it's negative 2/3, 4/3, 2/3, 0. Boom. Again, kind of the brute force way of doing it, but again, you can just do it in Mastham.
Both top sections will have the same.
Pretty much, yeah, that's a great point. You ought to try it, but yeah, they'll be the same. One of the reasons why they'll be the same is because of symmetry. What do you think? So, okay, here, let me follow up that with another question. If I were to take influence line AB and mirror it, what influence line would that be? This one right here, right? Make sense? It tells you where a moving load needs to be to generate worst case response. If I want to generate worst case response in this member, I put the load there. If I want to generate worst case response in this member, I put the load there. Now what we have yet to do is discuss specifically how to use them. But I will talk about that on Friday. But here's the spoiler alert. For concentrated loads, you multiply the load by the value on the influence line, and that will give you the response. And for distributed loads, you take the distributed load and multiply it by the associated area under the influence line, and it will tell you the associated response. And the beauty of an influence line is that I have right here the influence line for member AB. What that means is I now know the response of member AB to any load anywhere. No need to solve this truss 100,000 times. You tell me loads on joints, I'll tell you the answer. Now, this is limited to vertical loads. As soon as you start talking about horizontal loads, this all goes away. But influence lines are not meant to be a tool to assess loads moving like that. They're meant to be assessing loads like this because they are originally developed for bridges, right? That's what they're for. So they are only for transverse moving loads. But that's the only time you'd ever really need them anyways. The other thing I will mention, theoretically, they work for triangular loads, but we as engineers don't really ever deal with moving triangular loads. The only moving loads we deal with are point loads and distributed loads, something we will investigate and discuss over the next couple of days. Any questions? Right now, I just want you to learn how to draw them. We'll start using them on Friday. That's all I've got, everybody. I will see you all on Friday.